Hello, my name is Paul Geyer, and I'm here to chat with you today about foundation design for equipment, vibrations, and seismic loadings. This is what I'll be talking about today, kind of the chapters in the book, if you will. Single degree of freedom, damped, forced systems, foundations on elastic soils, wave transmission, attenuation, and isolation, evaluation of S-wave velocity in soils, and settlement and liquefaction. By way of introduction, this is just a little bit about me and what I've been doing for the last few decades. Vibrations caused by steady state or transient loads may cause settlement of soils, excessive motions of foundations or structures, or discomfort or distress to personnel. Some basic design factors for dynamic loading are treated in this discussion. Design of a foundation system incorporates the equipment loading, subsurface material properties, and geometrical proportions in some analytical procedure. Some limiting values of vibration criteria for machine structures and personnel have been described in terms of frequency and peak amplitudes of acceleration, velocity, or displacement. For structural safety during blasting, limit peak velocity to 2 inches per second and peak acceleration to 0.1 Gs for frequencies exceeding 3 cycles per second. These limits may occasionally have to be lowered to avoid being excessively annoying to people. For equipment vibrations, limiting criteria consist of a maximum velocity of 1 inch per second up to a frequency of about 30 cycles per second and a peak acceleration of 0.15 Gs above this frequency. However, this upper limit is for safety only, and specific criteria must be established for each installation. Usually, operating limits of equipment are based on velocity criteria. Greater than 0.5 inches per second indicates extremely rough operation and machinery should be shut down. Up to 0.10 inches per second occurs for smooth, well-balanced equipment, and less than 0.01 inches per second represents very smooth operation. Peak velocity criteria for reaction of personnel to steady state vibrations. Peak velocities greater than 0.1 inches per second are troublesome to some persons, and peak velocities of 0.01 inches per second are just barely noticeable to people. It's significant that persons and machines respond to equivalent levels of vibration. Furthermore, persons may notice vibrations that are about 1/100th of the value related to safety of structures. Vibrations of foundation soil systems can adequately be represented by simple mass spring Dashpot systems. The model for this simple system consists of a concentrated mass M supported by a linear elastic spring with a spring constant of K and a viscous damping unit or Dashpot having a damping constant C. The system is excited by an external force, i.e. Q equal to Q sub O times sine Wt, in which Q sub O is the amplitude of the exciting force, W is equal to 2pF sub O is the angular frequency in radians per second, with F sub O the exciting frequency in cycles per second, and T is the time in seconds. If the model is oriented appropriately, motions will occur in the vertical or Z direction only, and the system has 1 degree of freedom. 1 coordinate direction, Z, is needed to describe the motion. The magnitude of dynamic vertical motion, A sub Z, depends upon the magnitude of the external excitation, Q, the nature of Q sub O, the frequency F sub O, and the system parameters, M, C, and K. These parameters are customarily combined to describe the natural frequency as follows and indicated by equation 1. and the damping ratio is indicated by equation 2, both on slide 9. The dynamic response of the system when the exciting force is generated by a rotating mass is calculated using equation 3 on slide 10, where m sub E is the total rotating mass, E is the eccentricity, and F sub O is the frequency of oscillation in cycles per second. The ordinate m sub z relates the dynamic displacement a sub z to m sub e times E divided by m. The peak value of the response curve is a function of the damping ratio and is given by the following expression, which is equation 4 indicated on slide 11. For small values of d, this expression becomes 1/2 d. These peak values occur at frequency ratios as indicated by the formulas below on slide 11. With regard to foundations on elastic soils and foundations on elastic half space, for very small deformations, assume soils to be elastic materials with properties. Therefore, theories describing the behavior of rigid foundations resting on the surface of a semi-infinite homogeneous isotropic elastic body have been found useful for study of the response of real footings on soil. The theoretical treatment involves a circular foundation of radius r sub o on the surface of the ideal half space. This foundation has 6 degrees of freedom, 1 through 3 translation in the vertical z or in either of 2 horizontal xy directions, 4 is torsional or yawing rotation about the vertical z-axis, or 5/6 rocking pitching rotation about either of the 2 horizontal xy axes. A significant parameter in evaluating the dynamic response in each type of motion is the inertial reaction of the foundation. For translation, this is simply the mass, m is equal to W divided by G, whereas in the rotational modes of vibration it is represented by the mass moment of inertia about the axis of rotation. For torsional oscillation about the vertical axis it is designated as I sub q, whereas for rocking oscillation it is I sub y. For rotation about the axis through a diameter of the base of the foundation. If the foundation is considered to be a right circular cylinder of radius r sub o, height h, and unit weight y, expressions for the mass and mass moments of inertia are given by equations 6, 7, and 8 indicated on slide 14. Theoretical solutions describe the motion magnification factors m or ml, for example, in terms of a mass ratio b sub z and a dimensionless frequency factor a sub o. Table 1 lists the mass ratios, damping ratios, and spring constants corresponding to vibrations of the rigid circular footing resting on the surface of an elastic semi-infinite body for each of the modes of vibration. Introduce these quantities into equations given above to compute resonant frequencies and amplitudes of dynamic motions. The dimensionless frequency a sub o for all modes of vibration is given by equation 9 on slide 15. The variation of the damping ratio d with the mass ratio b may be noted for the 4 modes of vibration. Note that d is significantly lower for the rocking mode than for the vertical or horizontal translational modes. Using the expression m is equal to 1 divided by 2d for the amplitude magnification factor and the appropriate d, it is obvious that m can become large. For example, if b sub y is equal to 3, then d sub y is equal to 0.02, and m is equal to 1 divided by 2 times 0.02 equals 25. Table 1 indicates the mass ratio, damping ratio, and spring constant for rigid circular footings on the semi-infinite elastic body. The theoretical solutions described above treated a rigid foundation with a circular contact surface bearing against the elastic half space. However, foundations are usually rectangular in plan. Rectangular footings may be converted into an equivalent circular footing having a radius r sub o determined by the following expressions indicated on slide 17 as equations 10 for translation in z or x directions, equation 11 for rocking, and equation 12 for torsion. In equations 10, 11, and 12, 2c is the width of the rectangular foundation along the axis of rotation for rocking, and 2d is the length of the foundation in the plane of rotation for rocking. Two values of r sub o are obtained for rocking about both x and y axes. Embedment of foundations a distance d below the soil surface may modify the dynamic response depending upon the soil foundation contact and the magnitude of d. If the soil shrinks away from the vertical faces of the embedded foundation, no beneficial effects of embedment may occur. If the basic evaluation of foundation response is based on a rigid circular footing of radius r sub o at the surface, the effects of embedment will cause an increase in resonant frequency and a decrease in amplitude of motion. These changes are a function of the type of motion and the embedment ratio d divided by r sub o. For vertical vibrations, both analytical and experimental results indicate an increase in the static spring constant with an increase in embedment depth. Embedment of the circular footing at a distance d divided by r sub o less than 1 produces an increase in the embedded spring constant k sub zd, which is greater than kz, table 1, by kzd divided by kz at 1 plus 0.6 d divided by r sub o. An increase in damping also occurs, for example, as indicated by the equation on slide 19. And these two approximate relationships lead to an estimate of the reduction in amplitude of motion because of embedment according to the formula indicated on slide 19. This amount of amplitude reduction requires complete soil adhesion at the vertical face, and test data often indicated less effect of embedment. Test data indicate that the resonant frequency may be increased by a factor of up to 1 plus 0.25 times d divided by r sub o because of embedment. The influence of embedment on coupled rocking and sliding vibrations depends on the ratio BW divided by BX, refer to table 1. For BW divided by BX at 3.0, the increase in natural frequency due to embedment may be as much as 1 plus 0.5 times d divided by r sub o. The decrease in amplitude is strongly dependent upon the soil contact along the vertical face of the foundation, and each case should be evaluated on the basis of local soil and construction conditions. With regard to the effect of finite thickness of elastic layer, deposits of real soils are seldom homogeneous to significant depths. Thus, theoretical results based on the response of a semi-infinite elastic media must be used with caution. When soil layers are relatively thin with respect to foundation dimensions, modifications to the theoretical half-space analyses must be included. Generally, the effect of a rigid layer underlying a single elastic layer of thickness H is to reduce the effective damping for a foundation vibrating at the upper surface of the elastic layer. This condition results from the reflection of wave energy from the rigid base back to the foundation and to the elastic medium surrounding the foundation. For vertical or torsional vibrations or a rigid circular foundation resting on the surface of the elastic layer, it has been established that a very large amplitude of resonant vibrations can occur if V sub S divided by F sub O is greater than 4H. Equation 13 on slide 21. In equation 13, V is the shear wave velocity in the elastic layer and F sub O is the frequency of footing vibrations. When the conditions of equation 4 occur, the natural frequency, equation 1, becomes the important design criterion because at that frequency, excessive dynamic motion will occur. To restrict the dynamic oscillation to slightly larger than the static displacement, the operating frequency should be maintained at 1/2 or less of the natural frequency. The relative thickness, expressed by the ratio H divided by R sub O, also exerts an important influence on foundation response. If H divided by R sub O is greater than about 8, the foundation on the elastic layer will have a dynamic response comparable to that for a foundation on the elastic half space. For H divided by R sub O less than 8, geometrical damping is reduced and the effective spring constant is increased. The values of spring constant K in Table 1 are taken as reference values, and Table 2 indicates the increase in spring constant associated with a decrease in thickness of the elastic layer. Values of the increase in spring constants for sliding and for rocking modes of vibration will tend to fall between those given for vertical and torsion for comparable H divided by R sub O conditions. In general, vertical and torsional vibrations can occur independently without causing rocking or sliding motions of the foundation. To accomplish these uncoupled vibrations, the line of action of the vertical force must pass through the center of gravity of the mass and the resultant soil reaction, and the exciting torque and soil reaction torque must be symmetrical about the vertical axis of rotation. Also, the center of gravity of the foundation must lie on the vertical axis of torsion. When horizontal or overturning moments act on a block foundation, both horizontal sliding and rocking vibrations occur. The coupling between these motions depends on the height of the center of gravity of the machine foundation above the resultant soil reaction. A lower bound estimate of the first mode of coupled rocking and sliding vibrations can be obtained from equation 14 indicated on slide 24. In equation 14, the resonant frequencies in the sliding X and rocking Y motions can be determined by introducing values from table 1 into equations 1 and 5. Note that equation 14 becomes less useful when d sub x is greater than about 0.15. The first mode resonant frequency is usually most important from a design standpoint. Table 2 indicates values of K sub L divided by L for elastic layer, K taken from Table 1. Vibrations are transmitted through soils by stress waves. For most engineering analyses, the soil may be treated as an ideal homogeneous isotropic elastic material to determine the characteristics of the stress waves. Two types of body waves may be transmitted in an ideal half space: compression P- waves and shear S- waves at the surface of the half space. A third wave, known as the Rayleigh wave, R, or surface wave, will be transmitted. The characteristics that distinguish these three waves are velocity, wavefront geometry, radiation damping, and particle motion. The distance from the footing to each wave is drawn in proportion to the velocity of each wave. The wave velocities can be computed from the following. P wave, S wave, and R wave are calculated using equations 15, 16, and 17 on slide 26, with the components of these formulas being as indicated on this slide. The P and S waves propagate radially outward from the source along hemispherical wave fronts, while the R wave propagates outward along a cylindrical wavefront. All waves encounter an increasingly larger volume of material as they travel outward, thus decreasing in energy density with distance. This decrease in energy density and its accompanying decrease in displacement amplitude is called geometrical damping or radiation damping. The particle motions are as follows. For the P wave, a push-pull motion in the radial direction. For the S wave, a transverse motion normal to the radial direction. And for the R wave, a complex motion which varies with depth and which occurs in a vertical plane containing a radius. At the surface, R wave particle motion describes a retrograde ellipse. In a layered medium, the energy transmitted by a body wave splits into 4 waves at the interface between layers. 2 waves are reflected back into the first medium and 2 waves transmitted or refracted into the second medium. The amplitudes and directions of all waves can be evaluated if the properties of both media and the incident angle are known. If a layer containing a lower modulus overlies a layer with a higher modulus within the half space, another surface wave known as a love wave will occur. This wave is horizontally oriented S wave, whose velocity is between the S wave velocity of the layer and of the underlying medium. The decay or attenuation of stress waves occurs for 2 reasons: geometric or radiation damping and material or hysteretic damping. An equation including both types of damping is indicated on slide 29 as equation 18, with the components of that formula also indicated on slide 29. The isolation of certain structures or zones from the effects of vibration may sometimes be necessary. In some instances, isolation can be accomplished by locating the site at a large distance from the vibration source. The required distance, R sub 2, is calculated from equation 18. In other situations, isolation may be accomplished by wave barriers. The most effective barriers are open or void zones like trenches or rows of cylindrical holes. Somewhat less effective barriers are solid or fluid-filled trenches or holes. An effective barrier must be proportioned so that its depth is at least 2/3 the wavelength of the incoming wave. The thickness of the barrier in the direction of wave travel can be as thin as practical for construction considerations. The length of the barrier perpendicular to the direction of wave travel will depend upon the size of the zone to be isolated, but should be no shorter than 2 times the maximum planned dimension of the structure, or 1 wavelength, whichever is greater. The key parameter in a dynamic analysis of soil foundation system is the shear modulus G. The shear modulus can be determined in the laboratory or estimated by empirical equations. The value of G can also be computed by the field-measured S-wave velocity and equation 16. The shear modulus and damping for machine vibration problems correspond to low shear strain amplitudes of the order of 1 to 3 times 10 to the minus 4%. These properties may be determined from field measurements of the seismic wave velocity through soil or from special cyclic laboratory tests. S-wave velocity tests are preferably made in the field. Measurements are obtained by inducing a low-level seismic excitation at one location and measuring directly the time required for the induced S-wave to travel between the excitation and pickup unit. Common tests are described in geotechnical engineering literature. Table 3 indicates attenuation coefficients for earth materials. A problem in using seismic methods to obtain elastic properties is that any induced elastic pulse, blast, impact, etc., develops three wave types previously discussed, P, S, and R waves. Because the velocity of all seismic waves is hundreds of feet per second and the pickup unit detects all three wave pulses plus any random noise, considerable expertise is required to differentiate between the time of arrival of the wave of interest and the other waves. The R wave is usually easier to identify, being slower, it arrives last. Traveling near the surface, it contains more relative energy. Because R and S wave velocities are relatively close, the velocity of the R wave is frequently used in computations for elastic properties. Because amplitudes in seismic survey are very small, the computed shear and Young's modulus are considerably larger than those obtained from conventional laboratory compression tests. The shear modulus G may be calculated from the S, approximately the R wave velocity, using equation 19 on slide 34, where the properties of the components in the equation are as indicated on slide 34. This equation is independent of Poisson's ratio. The V sub S value is taken as representative to a depth of approximately 1/2 wavelength. Alternatively, the shear modulus can be computed from the P wave velocity and Poisson's ratio. Equation 20 on slide 35. The use of this equation is somewhat limited because the velocity of a P wave in water is approximately 5,000 feet per second, approximately the velocity in many soils, and Poisson's ratio must be estimated. For saturated or near saturated soils, mu of 0.5 is appropriate. Low shear strain amplitude, i.e. less than 10 to the minus 2%, shear modulus data may be obtained from laboratory tests and usually involve applying some type of high-frequency forced vibration to a cylindrical sample of soil and measuring an appropriate response. Some types of tests allow the intensity level of the forced vibration to be varied, thus yielding moduli at different shear strains. High strain level excitation in the range of 0.01 to 1.0% may be achieved by low frequency cyclic loading triaxial compression tests on soil samples. The modulus, damping, and strain level for a particular test are calculated directly from the sample response data. The usual assumption for calculating the modulus and damping from forced cyclic loading tests on laboratory samples is that at any cyclic strain amplitude, the soil behaves as a linear, elastic, viscous, damped material. Either shear or normal stress cyclic excitation may be used. The shear modulus is calculated from the slope of the peak-to-peak secant line. The damping is computed from the area of the hysteresis loop, and the strain level is taken as the single amplitude, 1/2 the peak-to-peak amplitude or origin to peak value, cyclic strain for the condition during that cycle of the test. This assumption is usually made in most soil dynamics analyses because of the low vibration amplitudes involved. If the cyclic hysteresis loops are obtained from triaxial test specimens, the resulting modulus will be the stress-strain modulus E. If the tests involve simple shear or torsion shear such that shear stresses and strain are measured, the resulting modulus will be the shear modulus G. In either case, the same equations apply. The shear modulus G can be computed from the stress-strain modulus and Poisson's ratio using equation 21 on slide 38. The shear strain amplitude AE may be computed from the axial strain amplitude E and Poisson's ratio as indicated by equation 22 on slide 38. For the following special case of saturated soils, Poisson's ratio is 0.5, which leads to the following formulas indicated at the bottom of slide 38. Empirical correlations from many sets of data have provided several approximate methods for estimating the S-wave velocity and shear modulus for soils corresponding to low strain excitation. For sand and gravels, calculate the low strain shear modulus using equation 24 on slide 39 with the values for k sub 2 and sigma sub 0 as defined on slide 39. For cohesive soils such as clays and peat, the shear modulus is related to S sub u as indicated by equation 25 on slide 40. For clays, k sub 2 ranges from 1500 to 3000. For peats, k sub 2 ranges from 150 to 160, limited database for the peats. In the laboratory, the shear modulus of soil increases with time even when all other variables are held constant. The rate of increase in the shear modulus is approximately linear as a function of the log of time after an initial period of about 1000 minutes. The change in shear modulus dg divided by the shear modulus at 1000 minutes g sub 1000 is called the normalized secondary increase. The normalized secondary increases range from nearly 0% per log cycle for coarse sands to more than 20% per log for sensitive clays. For good correlation between laboratory and field measurements of shear modulus, the age of the in situ deposit must be considered, and a secondary time correction applies to the laboratory data. Critical damping is defined by equation 26 on slide 41, where K is the spring constant of the vibrating mass and M represents the mass undergoing the vibration, weight divided by gravity. Viscous damping of all soils at low strain level excitation is generally less than about 0.01% of critical damping for most soils, or D equal to or less than 0.05 as indicated by equation 27. It's important to note that this equation refers only to material damping and not to energy loss by radiation away from a vibrating foundation, which may also be conveniently expressed in terms of equivalent viscous damping. Radiation damping in machine vibration problems is a function of the geometry of the problem rather than of the physical properties of the soil. The effect of increasingly higher strain levels is to reduce the modulus and increase the damping of the soil. Shear modulus and damping values at high strains are used mainly in computer programs for analyzing the seismic response of soil under earthquake loading conditions. The various empirical relations for modulus and damping pertain to sands and soft, normally consolidated clays at low to medium effective confining pressures in the range of about 100 feet of overburden. Stiff, unconsolidated clays in all soils at high effective confining pressure exhibit lower values of damping and higher values of modulus, especially at high strain levels. As a maximum, the modulus and damping values for stiff or strong soils at very high effective confining pressures correspond to values pertaining to crystalline or shale type rock. Repeated shearing strains of cohesionless soils cause particle rearrangements. When the particles move into a more compact position, settlement occurs. The amount of settlement depends on the initial density of the soil, the thickness of the stratum, and the intensity and number of repetitions of the shearing strains. Generally, cohesionless soils with relative densities greater than about 75% should not develop settlements. However, under 106 or 107 repetitions of dynamic loading, even dense sands may develop settlements amounting to 1 to 2% of the layer thickness. To minimize settlements that might occur under sustained dynamic loadings, the soil beneath and around the foundation may be pre-compacted during the construction process by vibroflotation, multiple blasting, pile driving, or vibrating rollers acting at the surface. The idea is to subject the soil to a more severe dynamic loading condition during construction than it will sustain throughout the design operation. The shearing strength of saturated cohesionless soils depends upon the effective stress acting between particles. When external forces cause the pore volume of a cohesionless soil to reduce the amount V, pore water pressures are increased during the time required to drain a volume of V of water from the soil element. Consequently, pore pressure increases depend upon the time rate of change in pore volume and the drainage conditions, permeability, and available drainage paths. When conditions permit the pore pressure to build up to a value equal to the total stress on the failure plane, the shear strength is reduced to near zero and the mixture of soil grains and water behaves as a liquid. This condition is true liquefaction, in which the soil has little or no shearing strength and will flow as a liquid. Liquefaction or flow failure of sands involves a substantial loss of shearing strength for a significant length of time that large deformations of soil masses occur by flow as a heavy liquid. Soil deposits that have a history of serious liquefaction problems during earthquakes include alluvial sand, aeolian sands and silts, beach sands, reclaimed land, and hydraulic fills. During initial field investigations, observations that suggest possible liquefaction problems in seismic areas include low penetration resistance, artesian heads or excess pore pressures, persistent inability to retain granular soils in sampling tubes, and any clean, fine, uniform sand below the groundwater table. The liquefaction potential of such soils for structures in seismic areas should be addressed unless they meet one of the criteria, in the event that boundaries are large enough to preclude the development of excess pore pressures. And that brings us to the conclusion of this brief discussion of foundation design for equipment vibration and seismic loads. I hope that some of this information has been of value to you and that it will permit you to move forward and deal with problems of this and design problems of this sort when they come across your desk in the future. With that, let me thank you again very much for letting me chat with you, and have a nice rest of the day.